What we see on the screen here is a series of figures which represent an experiment which we're going to carry out, which will be demonstrated along the lines of a mathematical idea. What we're looking at is the chances or potential for life in this galaxy. So first of all, we're going to limit ourselves to the Milky Way rather than everything beyond that. The second thing that we'll assume for the purpose of this is that life exists only on planetary systems. Humanity lives on Earth, and Earth is a satellite that revolves around our Sun, planetary system. For all we know, life could exist in Oort clouds, on moons, on satellites, in any form that we know, but we'll assume, for the purposes of this, on planetary systems orbiting stars. The size of our galaxy is 100,000 light years in diameter. That means traveling at the speed of light, which is 3 times 10 to the 8 meters per second, or 300,000 kilometers per second, which is the upper limit, hypothetically, that anything can travel at in our universe. It would take 100,000 years to go from one side of the galaxy to the other. The best estimate for the number of stars within our galaxy, the Milky Way, is 100 billion. That's a 100 followed by 9 zeros, or a 1 followed by 11 zeros. I'm going to scale it up to the upper end of the estimate, which is 400 billion, so that we can assume that there are more stars than there really may be in our galaxy. And the next important assumption I'm going to make is about the distances between any two stars in our galaxy. Our galaxy is 100,000 light years in diameter. That means the furthest that any two stars could be from each other within the Milky Way is 100,000 light years. So I'm going to assume any two stars picked at random are 100,000 light years apart, maximizing the distance between them, when the vast majority will have distances far less than that. The reason for that will become apparent soon enough. So that's the setup for this thought experiment. Now, what we're looking at on screen represents a machine of some kind that we want to build that's designed to populate every star system within the Milky Way. We build one machine, and it's sent from Earth to the nearest star, remembering that all stars are equally far away from each other, the maximum distance of 100,000 light years. Once this machine arrives at the nearest star, it stays there and it generates 2 replicas. 2 replicas then leave to populate 2 other star systems, and they then follow the same course, each one generating 2 more. So in the next iteration we have 4 of these machines. They then go out and populate 4 more star systems, and each one generates 2 replicas, and so line by line as we go down the page, the numbers double with each successive iteration. So effectively what we have here is an exponential growth function, and it's modeled by the following. Y is equal to a to the power of x, where a is the base and x is our exponent. In this case, a is equal to 2, because we're multiplying with each iteration by 2. But despite that, this curve grows very rapidly. The formula for the number of figures in each row is given by 2 to the n minus 1. So in the first row we have 1 figure, and that's modeled by 2 to the power of n minus 1, 2 to the power of 1 minus 1, 2 to the 0, which equals 1. In the second row we have 2 figures, which is modeled by 2 to the power of 2 minus 1. That's 2 to the power of 1, which equals 2, and so on. Before I go any further, if you maximize this video so that it plays full screen on your laptop, you would be able to see that the distance between the 2 figures in line 2 is approximately 20 centimeters. If I had kept that distance constant between every 2 figures line by line as we move down the page, which I couldn't do because I was cramming more figures into each line, then by the time we got down to the 8th line, where there is 2 to the power of 7, which is 128 of those figures crammed together, then the distance from the leftmost figure to the rightmost figure would have been 25 meters. By the time we go 7 lines below that to the 15th line, then the distance between the leftmost figure and the rightmost figure would be 3,276 meters, just over 3 kilometers. By the time we go 5 lines beneath that, the 20th line, the same distance would be approximately 105 kilometers. By the time we go 10 lines below that, the 30th line, the distance from the leftmost figure to the rightmost figure would now be 215,000 kilometers, which is more than half the distance from the Earth to the Moon. 10 lines below that, the 40th line, the distance from the leftmost figure to the rightmost figure would now be approximately 215 million kilometers. That's more than the distance between the Earth and the Sun. So the point that I'm making here is that these numbers, iteration by iteration, rapidly increase.